Kia ora Year 12 and Year 11. This is an old exam question from the 2015 summer A-level paper. It's a parametric differentiation question, and then it's got a bit of iterative solutions in it. So if you're watching this when you get a notification that the video's gone up, just don't worry about it until we're finished with Trig. I'm just starting to try to get a little bit ahead of myself. And we haven't done the content for the very last part of this question yet. I am going to try and squeeze it into the video, but I'm going to go quite slowly through it. Okay, so let's start off by having a look at what we've got. We've been given a picture, so that's always good. So here's my curve, and the curve is defined with two parametric equations. Right, so we're getting used to that. We've got x depends on t, and y depends on t. So remember, that's like having t affecting x and y, which means that these two things are linked, even though we haven't written y in terms of x or x in terms of y. So the first thing we have to do is to find the gradient of the curve at the origin. So as usual, what that means is find dy by dx at the point 0, 0. And then after we've done that, we're told that at some point p here, the value of the parameter is little p, and the gradient at that point is 1/2. So now we're going to solve dy by dx equals 1/2, and we're going to show something about this value of p. Okay, and then the last bit is how can we solve this very horrible equation? Now you can see that this step of the question here is going to be very easy because it's only 1 mark, but this is going to be quite tedious. I'll just warn you. Iterative methods are not exactly an entertaining maths. So let's do the cool part first, which is finding the gradient, and I'll work on that down here. So we've got x is equal to 2 times the natural log of t plus 2, and y is equal to a cubic t cubed plus 2t plus 3. So we know that dy by dx is equal to dy by dt times dt by dx, which we can write as y dash over x dash. Now, dy by dt is equal to 3t squared plus 2, and dx by dt equals, well, I'm differentiating a natural log, so it's going to be 1 over that times 2. Okay, so 2 is just my scalar multiple, so that just flows through. So what do we get for dy by dx? Well, dy by dx is equal to 3t squared plus 2 divided by 2 over t plus 2, which gives me 3t squared plus 2 times t plus 2 over 2, right, dividing by a fraction. Now, we don't need to do anything more with that. There's no need to expand it or try and muck around with it. All we have to do now is to say, where is the origin, right? Because the question asked us not for the gradient of the curve when t equals 0, but for the gradient of the curve here. And we don't know what the value of t is at the origin. So we have to figure that out now. So now we're working back to what are x and y? Well, x is equal to 2 log of t plus 2, and y is equal to t cubed plus 2t plus 3. So let's focus on this equation. So when is x 0? When is x equal to 0? 0 is equal to 2 times the natural log of t plus 2, and we know that we need to have, so the natural log of 1 is going to give me 0. So solving this properly, we get 0 equals log of t plus 2. Sorry for the background singing, it's not me. And now we've got t plus 2 must equal 1, so t equals -1. Right, so just remember, very useful fact about logs that you will need over and over is that the log of 1 is 0, no matter what the base is. Now we can check that by chucking it in up here and making sure that we do get a y coordinate of 0 as well. right? So negative 1 cubed minus 2 plus 3 equals 0. All right, so that's good. So what that means is that when t equals negative 1, we have the point 0, 0. So now we need to take dy by dx and figure out what that is at a t value of negative 1. So here's my expression for dy by dx. Now I'm going to substitute in negative 1. So it'll be 3 plus 2, whoops, big bracket by mistake, never mind. And then I have negative 1 plus 2 here, divided by 1, which gives me 5 times 1. Where's my 2 gone? I've lost the 2. That should be a 2. So 5 times 1 over 2, which is 5 over 2. Right, so that was worth 5 marks. So, okay, let's just go over those steps again. Let's go back to the question and look at the big picture. Right, so we had a diagram here. Here's the diagram, and we had to find the gradient. So first we found a general equation for the gradient, and then we had to evaluate the gradient here. The key to this question was understanding that at the origin, that does not mean that t is 0, right? Because t of 0 here would give me x equals 2 log of 2, right? Which is definitely not 0. So we had to figure out where will we get the origin. So we're solving these to find the value of the parameter t. And when we did that, we got t equals negative 1. Okay, now the next part of the question is actually easier than that. It's to show that at a point P, the gradient of the curve is equal to 1/2. And we're told that the value of the parameter is P. Okay, so what can we do? Well, we know that the derivative here, dy by dx, is given by this for any value of the parameter. Right, so that's dy by dx. But we know that when our parameter is p, so when we replace t with p, that the value is equal to 1/2. So instead of t here, we substitute in p, and we get 1/2. And what we have to show is that p is equal to this. So it's just really a really easy little rearranging exercise. Okay, I'm just going to erase this here because I've just chopped up this recording because I mucked it up. So just hang on while I fix that up. So here we are, we've got this expression up here, and we've got to show that we can get this equation out of it. So we're going to multiply through both sides by 2, and we get this 3p squared plus 2 times p plus 2 is equal to 1. And now you can see in here that we've divided through, or the examiner has divided through by 3p squared plus 2. So we're going to do that on both sides here. And we get p plus 2 is equal to 1 over 3p squared plus 2. And so p is equal to 1 over 3p squared plus 2 minus 2, right, as required. Okay, so you're probably wondering what was the whole point of that? Well, the point is that we've now found that at that point P on the curve, so here's the curve and here's point P, that the value of the parameter was equal to little p. But the way we've gone about it means that we've got an equation that is really, really hard to solve. Okay, so this is not a quadratic or a disguised quadratic or anything that we can do easily. So what we have to turn to, instead of analytical algebraic methods, is stuff called iterative methods, which is basically where we guess and check a value and then try to get closer and closer. So I'm going to do that now because we've got 6 minutes of the video left, and it comes through in chapter 6 of the textbook, and we'll be looking at it soon in class. But it's quite easy once you get the hang of it. So let's have a look at what we're going to do. I'm going to go back up to the graph at the start. So here's my point, right? This is P, and we're trying to figure out what is the value of this parameter little p. And we've figured out that it has to fit this equation in here, just trying to clean up all the working. So we've got down to this equation. We're going to try and find a number for p, but we have to have a starting point. So we're just going to take potluck and guess, and I'm going to start with p equals -1, and we know that p equals -1 up here, so we know that's going to be wrong, but we're going to try and gradually creep along until we satisfy this equation. So the idea is we start with a value and then we just keep on updating. So we're going to rewrite our formula to say, let's say that I'm going to update my value of p based on what I get out of the right hand side. So we're going to have a starting value of p, and we're going to put it into the right hand side and see what new p value we get out. And hopefully they're going to get closer and closer together. And then we're going to do it again, but we're going to use this value as my starting point. So the next step will be to go like this. And we're going to keep on doing that until the two values of p get extremely close together. And I think in this question they said go until it's correct to 4 decimal places. So for this you're going to need your calculator. And where are we going to start? We're going to do a table. That's the first bit of advice. So we're going to make this Pn, and this is going to be my new Pn, so Pn plus 1. So P0 is equal to -1. So we put that into our formula, and we're going to get 1 over 3 times -1 squared, so it's going to be 1 over 3 plus 2, take away 2. So that gives me -1.8. So that's my new updated guess for P. And you can see that these things are not equal yet, right? We want this to equal this because that's my solution. That's the value of P that makes the two sides the same. So now we put in P1 is equal to -1.8. So do this on your calculator. And then when I substitute that into there, I'm going to get out -1.91468. Now carry a few extra decimal places here. Then when we update that, that's my new starting point. What comes out? Well, I get -1.92307, and then P3, I put in that number, -1.92307, and we get out this. And you can see that these numbers are getting really quite close together. So P4, when I put in this, I'm so close to having matching numbers. I have -1.92367. This is strangely entertaining if you're ever really bored. But compared to most of the maths in the course, I find it pretty tedious. But it's actually how a whole lot of computers and calculators work, right? So, good to understand. So there we go. Once we've done 5 iterations, we can see that this is what we call convergence to 5 to 4 decimal places. So let's look at what we've said. Well, we've now got the situation where P of n plus 1 is equal to this value when we put in P. So we've got very, very close to, we've got within 4 decimal places of equality here, right? So we say that it's converged to 4dp. Okay, that's all for now. As I said, hopefully you haven't watched till the end because I want you thinking about the trig internal, and we'll get on to the second half of this question later on this week.